This is my part 1 submission for homework 3 for my mass and energy balance course. The problem that we were given is we have a container that has 1 kilogram of water in it. So this is 1 kilogram of water. It's open to the atmosphere. It's initially at 298 Kelvin and 1 bar or 100,000 pascals. We then seal the container just like that, and we heat it up to a final pressure of 2 bar. Now we want to find the final temperature and the total volume of the container such that 0.3 moles of water are in the vapor phase. I have all of that outlined here. So our initial temperature is 298 Kelvin, initial pressure is 1 bar. We don't know our final pressure or our final temperature, but our final pressure is 2 bar. We want to find our final temperature and our volume such that the number of moles of water in the vapor phase is 0.3 moles. The key relationship between all of these figures is our ideal gas law, or PV equals nRT, where P is our pressure, V is our volume, N is the number of moles, R is a constant, and T is our temperature. And a big part of this is going to be the pressures that we work with. So the total pressure of everything inside of this container is going to equal the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of argon plus the partial pressure of water. And all of that together is going to equal the total pressure. Now, these first three partial pressures that I said are equal to the pressure of air because the air that we breathe in and out contains nitrogen, oxygen, and argon. And an important part of that is the mole fractions, or how much of each component is in our air. That's pretty universally known. So mole fraction of N2 is 78%, or 0.78. Of oxygen is 0.21, and of argon is 0.01. And that is what we're going to say makes up the entirety of our air. We know there's more stuff in there like carbon dioxide or methane or anything like that. But for simplicity's sake, we're just going to use those three. Now, this pressure of water here, we're going to say equals the pressure at a certain temperature of water. So the pressure of water at its vaporization phase. So instead of all the liquid, we're talking about the gas or the water vapor phase. Initially at this 298 degrees Kelvin, it's not going to be very much, but as we heat that up, more and more air is going to go into the vapor phase. So PH2O in the vapor phase at a certain temperature. And as our temperature goes up and down, that pressure of H2O will go up and down with it. Now, going back to our PV equals nRT, we can use this, say, for our initial pressure. Our initial pressure times our volume is going to equal the number of moles of air. The number of moles of water in the vapor phase is kind of negligible, so we will say N of air, and that is just the number of moles of N2 plus the number of moles of O2 plus the number of moles of argon, and then times R times our initial temperature, just like that. And if we want to solve for the number of moles of air, we can just manipulate this equation. So N air equals P initial V over R T initial, not T naught, just like that. And this is the equation or the set of equations that we will use when we go to Python in part 2 and solve this numerically. As we said at the very beginning, because of the number of constraints we have and the number of unknowns that we have, solving this algebraically would be very difficult, almost near impossible. So we have to do this via coding, which we're going to use Python, and solve it numerically. So part two, we will use what we discussed here in part one. We will implement it into Python and we will solve for the temperature, final, and for the volume of the container. That's so everything meets the requirements given in the problem.